In this video, we're going to cover the other set of techniques that are required for solving the more complicated polynomials. These are called the remainder theorem and the factor theorem. For those who don't know me, my name is Chris Heinazoni. I used to work as an engineer for a defense company, and I've since left that to start a career in tutoring. I make these videos so that VC students can do the best they can in math methods. With that out of the way, let's get into it. Up until now, you should be familiar with polynomial division already. And sometimes when you do a polynomial division, you get a remainder at the end. If all you care about is the remainder at the end, then it's not necessary for you to do the entire polynomial division. There is a shortcut, and that shortcut is called the remainder theorem. The remainder theorem states that any polynomial divided by some linear ax plus b has a remainder given by f of negative b over a. As a quick example, if we had this cubic divided by x minus 2, then the first step of doing the remainder theorem is just figuring out what is a and what is b. A is always going to be the coefficient on the x, which in this case is going to give us a equals 1. And b is always going to be the constant as part of the linear term, which in this case means that b is going to be negative 2. So to find the remainder, all we do now is sub in our values for a and b into the remainder theorem, and then whatever the result is the remainder, which in this case is 6. Another common application of the remainder theorem is that it can be used to give you an equation for solving unknowns, like this example here, where we know that if we are dividing by x minus 3, the remainder after division is going to be 17. We solve this kind of question in a very similar way to how we solved the previous question. We're just going to start by identifying what is a and what is b, which in this case a is going to be 1, since the coefficient on the x is 1, and b is going to be negative 3, since our constant is negative 3. Once again, we're going to sub that into the remainder theorem equation, but this time we're going to equate it to 17, since we know that's what the remainder should be. All we have to do from here is rearrange for k. This is just a linear equation, so there's nothing special here. It's just pure algebra. Once you simplify all the way, you're going to see that the result is going to be k equals 4. The factor theorem is actually an extension on the remainder theorem. Specifically, the factor theorem states that if your remainder is 0, then the linear term ax plus b must have been a factor of that polynomial. We've actually seen this before numerically. I know that 2 is a factor of 4 simply because 4 is divisible by 2. It is perfectly divisible by 2, there is no remainder after division, hence 2 is a factor of 4. The exact same thing is true for polynomials. After dividing by our linear term, we get no remainder. Remainder theorem equals 0. Let's see a few examples. The most straightforward application of the factor theorem is to just prove that your linear term is a factor of some polynomial. So all you're going to do is sub into the remainder theorem and equate it to 0, just like the factor theorem suggests. So we have to know what a and b is, which in this case, both of those terms are just going to be 1. We're then going to sub that into the remainder theorem and then just simplify the result. If we get 0 at the end, then we know that it is a factor. And sure enough, we did get 0, hence we can say that x plus 1 is a factor of that polynomial. The more common use of the factor theorem is to use it to find factors, rather than prove ones that already exist. These kinds of questions can almost be thought of as the reverse of the previous example. In the previous example, we had a factor and we had to prove that the remainder was 0. In this case, we don't know what the factor is, but we do know that the remainder should be 0. So, what do we actually do here? Well, we basically have to just guess what a and b are going to be through trial and error. Here's a few guidelines. The first suggestion is to just assume that a is going to be 1. This is going to be true of 99% of all questions because, as you'll soon see, the number of combinations that you have to guess are quite large, and that's just with a equals 1. If a could be anything, then the number of guesses are potentially limitless, and it would take forever. It wouldn't make for a very accessible test. So the assessors make life easier on you by just setting a equals 1. When we assume that a equals 1, our factor theorem is just going to become f of negative b equals 0. Much simpler. The next thing to do is figure out what b is through trial and error. Now you can still limit the number of possibilities by simply looking at factors of the constant at the end, which in this case means we're looking for factors of 6. Just don't forget both the positive and negative versions of those factors. Once we have that list, we're just going to test them from easiest to hardest until we get an answer of 0. That's all there is to it. Normally I would test 1 first, but since that's actually going to be the answer, we're going to test negative 1 first, just so you see what happens when you get an incorrect result. In this case, if you had subbed in negative 1, you would get a result of 8. Now, a remainder of 8 is not a remainder of 0, hence we need to test another factor. Now we're just going to test 1. And sure enough, as I said earlier, this does in fact equal 0. Now that we have our winning number, we need to equate it to negative b, since that's what the simplified version of the remainder theorem actually is. Remember, the whole point was to sub in numbers, and then those would be attributed to being the a and b values. We got away with simplifying it a little bit, since a equals 1. So, from direct comparison, we can see that negative b equals 1. Or, if we get b on its own, we're going to see that b equals negative 1. Now that we have the a term, which we know is 1, and the b term, which we know is negative 1, we just sub that into our linear, giving us x minus 1 as the factor. The reason we care so much about the factor theorem is because it allows us to factorize polynomials through polynomial division. In the previous example, we figured out that x minus 1 was a factor of our cubic. Now, because we know it's a factor, if we were to divide that cubic by that linear term, then we're going to get a perfect result. There's not going to be any remainder after division. So, if we go ahead and divide by x minus 1, we're going to get a quadratic, x squared minus x minus 6. Now, I've only presented a picture of what polynomial division looks like. If you need to review what that's like, I have a video linked above, so feel free to click that link to revise. So, if dividing f of x by x minus 1 gives you a quadratic, then you can actually rearrange that equation to get f of x on its own. Suddenly, what we've done is convert our cubic f of x into a factorized form. See how it's a product of two factors. This is really good because you need to solve cubics through null factor law. We don't have any other option. We've got two things that are multiplied together to give 0. That is the situation for null factor law. So all we're going to do from here is just factorize that quadratic. That's going to give us a sequence of 3 linear terms, which we set equal to 0, and then solve each of them individually. If you found this video helpful, then you should consider joining my free community. I host a Q&A call every week to personally help you through any of your specific questions, and you'll also get access to more resources like this, including written and recorded lecture content, as well as practice exams and SACs with detailed solutions. It's pretty cool, you should check it out. I'll see you there.